Alright, hello everyone, welcome back to another video. Today we want to cover the ratio test. Now the ratio test is like the Swiss Army knife of tests for convergence and divergence. We're going to be using the ratio test for the entirety of this unit for the rest of the unit. It's going to be our good friend. It's going to determine radius of convergence for our power series. So it's going to be a very helpful tool. So we're going to cover it today and we're going to go through a couple of examples. So let's start with the ratio test. Okay, so the definition for the ratio test is that if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n equals L, so if that absolute value equals L, so if we can evaluate the limit, and it's less than 1, then the series converges absolutely. And what we talked about in the last video is that if a series converges absolutely, then it will also just converge flat out. So now we have another case. So if the limit that I just stated is greater than 1, or it's infinite, well then our series is going to diverge. And then finally, if the ratio, the limit of that ratio, is equal to L, and that's equal to 1, then the test is inconclusive. So these are really the three main cases that you need to remember for the ratio test. If the limit is less than 1, then we converge. If it's greater than 1, it diverges. And if it's equal to 1, it's inconclusive. You should move on to a different sort of test. Okay, so let's do a couple of examples. Here's the first one. So determine if the series converges or diverges absolutely or conditionally. I actually kept the same problem statement from the last video because we use it so much. But the series we're looking at is n equals 1 to infinity, of negative 1 to the n times n cubed over 3 to the n. Okay, so we have this little alternating bit in there, so we know that when we take the absolute value of that, then we won't need to worry about that as much. So let's move on to the ratio test. So we are going to take the limit, or well, let's just find out what our absolute value is. We're going to find absolute value of a sub n plus 1 over a sub n. Now this is actually going to be fairly easy. We're going to take one term here, and then we're just going to add 1 wherever we see an n. And then we're going to divide it by just the standard term, and we're going to take the absolute value. Now, something important to note here is that I didn't want to write the compound fractions, so you need to remember the keep, change, flip rule from middle school or elementary school. And so you just flip over the when you're dividing by. That makes it easy, and there's going to be a lot of cross terms that will cancel out. Anyways, we get the absolute value of negative 1 to the n plus 1 times n plus 1 cubed over 3 to the n plus 1 times 3 to the n over negative 1 to the n times n cubed. Okay, so we take the absolute value of that, then our negative 1 terms are going to go away. So we're going to get n plus 1 cubed over 3 times n plus 1 times 3 to the n over n cubed. So now what we can do is we can actually take out a couple of terms. So if you notice here, we have this, this term here, 3 to the n plus 1 over 3 to the n, or 3 to the n over 3 to the n plus 1. So you can actually cancel out all of this here, and we can cancel out all but one of these, and then we get 1/3. And then also we can cancel out this other term because we're both cubed, so we can uncube them by taking the cube root. So we're going to get 1/3 over n plus 1 over n cubed. And we're going to simplify this out a little bit so that we can separate all of our fractions, because that's going to work out nicely for the limit. We get 1/3 times 1 plus 1 over n cubed. Okay, so now what we can do is we can take the limit. So if we take the limit, we get the limit as n approaches infinity of 1/3 times 1 plus 1 over n cubed. So what happens as n goes to infinity? Well, we have this 1 over n, and that's the only n that we have. So if we take that to infinity, then this guy is going to go to 0. So then we just get 1/3 times 1, because this cubed doesn't really matter to a 1. And we just get 1/3. 1/3 is obviously less than 1, so thus we can say that the series is absolutely convergent by the ratio test. Okay, let's move on to the next example. Determine if the series is convergent or divergent. Okay, so the series that we want to look at is kind of interesting. It's the series from n equals 1 to infinity of n to the n over n factorial. Now this is kind of interesting because both of these functions grow super largely, because n to the factorial is a really fast growing function, and so is n to the nth power. So we really want to know what's going to happen when we divide these. Are we going to diverge or are we going to converge? It's a little bit of a suspense. So let's take the ratio test. We can use the ratio test for this. So we take the absolute value of a sub n plus 1 over a sub n, and this turns out to be the absolute value, again, using that keep, change, flip law of n plus 1 to the n plus 1 power over n plus 1 factorial times n factorial over n to the n. Okay, so we can keep rearranging this, and we can also cancel out a lot of common factors. So what we are going to get is we are going to get very similar to what we got the last time, this sort of n plus 1 over n deal. So we get n plus 1 over n to the nth power. Again, we can break down the fraction. We get 1 plus 1 over n to the nth power. Now, this is something that's very interesting because when we take the limit of this, we actually get e. Now, this is something from compound interest that you might remember for continuous compound interest back in like elementary functions, but that number is e if we take the limit as n approaches infinity, 1 plus 1 over n to the nth power. It's going to be e. E is larger than 1, so thus we can say our series is divergent by the ratio test. Okay, so that's the ratio test. It's not super hard in its entirety. It's just the algebra that gets a little bit hairy when you're taking all those absolute values, and you also want to figure out what your limit converges to. Okay, so that's the ratio test. In the next video, we're going to talk about our last test for convergence, which is called the root test. It's a little bit of a lesser known test, but it is a good last line of defense. Thanks for watching. We'll see you then. Bye.